exponents. So an exponent is really just a shorthand for repeated multiplication. So when I write something like 2 to the 5th, what we mean by that is 2 times 2 times 2 times 2 times 2, which is equal to 32, but I don't really care about that at this moment. Or when I write, 6 to the 4th, I mean 6 times 6 times 6 times 6. So it's really just an abbreviation that allows us to write things without having to write a whole bunch of things. In a similar way, well, maybe not in a similar way, but radicals also have a very specific meaning. When I write the third root of 64, well, first of all, I should point out that the 3 is called the index. Not that we use that a whole lot. And this symbol is the radical symbol, or the root symbol, as we sometimes call it. And so exponents are shorthand for repeated notation, right? It's saying, what do you get when you multiply 2 by 2 by 2 by 2 by 2? Radicals are kind of the opposite of that. They say, okay, if I want to take the third root of 64, the question that I'm actually asking is, what number multiplied by itself 3 times whatever the index is equal to 64. That's what that is actually asking us for. So if that was a 5 there, they'd be asking what number do you multiply by itself 5 times 264. It's a less nice number. So that said, the cube root of 64 is 4, because 4 times 4 times 4 is equal to 64. In a similar way, the fourth root of 81 is equal to 3, because 3 times 3 times 3 times 3 4 times is equal to 81. And also the second root of 25. So for square roots, we don't usually write the 2 there, right? You could write the 2 as an index, but we often omit it. That's equal to 5, because 5 times 5 is equal to 25. So that's what roots and exponents mean. And then we have some rules surrounding them. I've already erased. Look at me being ahead of things. So here are some rules for working with exponents and radicals. And radicals? No, just exponents, actually. Well, yeah, and radicals. And it's actually there's one more rule in there that's not on there. So here's the first one. When you have two things with the same base multiplied together, we add the powers. So x to the a times x to the b is equal to x to the a plus b. It's called the additive law of exponents. So when you multiply two things together with the same base, you add the exponents. Again, this makes sense if you think about what it means. If you're multiplying 2 to the third times 2 to the fourth, 2 to the third means 2 times 2 times 2. 2 to the fourth means 2 times 2 times 2 times 2. And so that times that is just 2 multiplied by itself 7 times. Right? 2 times 2 times 2 times 2 times 2 times 2 times 2 is exactly 2 to the 7th, which is 2 to the 3 plus 4. We also have some other rules. I have x times y to the, actually I want to go to this other, let me go kind of down across whatever. If you're looking at the notes, I am. So if I have x to the a divided by x to the b is equal to x to the a minus b. It's very much the same rule as this, just a different version of it. If I have x times y to some power, I can distribute that power across multiplication. Did you have a question, Aaron? Okay, sorry, I thought I saw your hand go up. So that's going to equal x to the n times y to the n. We also have this one. If you have a power to a power, you multiply the power. So x to the a to the b is x to the a times b. An example of that would be something like 2 to the third to the fourth, right? That's 2 to the third times 2 to the third times 2 to the third times 2 to the third 4 times. But then we can add those powers. 3 plus 3 plus 3 plus 3 is 12, which is just 3 times 4. We also have, I'm going to throw in an extra one there that's not on this list. We have that the nth root of a number is the same as that number to the 1 over n power. So it's actually really kind of worth noting that radicals and exponents are the same things. It's just that we sometimes write them differently. So I could always, if I wanted to, right, instead of writing the third root of 64, I could totally write this as 64 to the 1/3. And I could write this as 81 to the 1/4. And I could write this as 25 to the 1/2. Right? You never have to use a radical really ever to express something. You could always use a power if you wanted to. And I will also point out that when we get to calculus, it often becomes convenient to write everything in terms of powers because of what we have to do with differentiation. So it's very, very good to be able to go easily back and forth between writing something as a radical and writing something as a power. And then we have two more things. We have that we can make this a little bit more complicated. X to the fractional power a over b, which I don't think I've written very nicely here. Let me try to write that again. X to the a over b power. There's a couple ways we can rewrite this. We can write this as the bth root of x to the a. And we can also write it as the bth root of x to the a. So if you have something to a fractional power, you can either raise it to the numerator part first and then take the denominator root, or you can switch it and do the denominator root part first and then the numerator power. And we'll definitely talk about some examples of this today. And then lastly, sorry, let me put this in the box too. The last one we have is that x to the negative n is equal to 1 over x to the n. And that actually comes up right here, right? If you wanted to, you could rewrite x to the a divided by x to the b as x to the a times x to the negative b. And then you could add those powers together to get exactly this part right here. Okay. So those are the rules, most of the rules we have for exponents and radicals. There's probably a few other kind of weird ones we're not mentioning. That's all right. So let's look at a couple examples of things. In fact, we'll start with one of my favorite examples. I want to evaluate -8 to the -2/3 power. So there's a couple ways to go about this. My preferred way is to think about doing the root part first, meaning the denominator part of the power, and then the numerator part after. So I really want to write this as -8 cube root all squared. Sorry, all to the -2. I could also, instead of writing the cube root, I could also write it as -8 to the 1/3 to the -2nd. All right, what's the cube root of -8? What number do you multiply it by itself 3 times to get -8?
-2.
Yeah, it is -2. So for odd roots, like a cube root or a 5th root or a 7th root, if you take an odd root of a negative number, you get a negative answer. If you take an odd root of a positive number, you get a positive answer. And for even roots, we can't take even roots of negative numbers and get positive results. And get real results, I mean, sorry. So we can only take even roots of positive numbers. So this is -2 to the -2nd, which I'm then going to rewrite as 1 over -2 to the +2nd. And the -2 squared is +4. Right? -2 squared is just -2 times -2. So it's 1 over 4. A different way of tackling this, not my preferred way, but it is another way. Some people like to think about, okay, I've got -8 to the -2/3. I want to take the third root of -8. So I need to think of -8 as some number cubed. So some people like to do this and say, oh, -8 is -2 cubed. And then when you have a power to a power, you multiply the powers. So this is going to be -2 to the 3rd times -2/3. 3 times -2/3 is -2. So I get -2 to the -2nd power. And I'm back in this spot here. That's equal to 1 over -2 squared. That's equal to 1/4. So either way of imagining is perfectly fine. Let me do it. Yeah. I'm going to be efficient with my time here. We can also look at simplifying some radicals. So if I want to simplify, say, the cube root of 32, the idea when you're asked to simplify a radical expression like this is to kind of pull out as much from the radical as possible. Meaning, if there's any cubic factors in there, I'm going to pull them out. So you could either think of this as just, what's the cube root of, I know that 8's a cubic number, and I know that 8's a factor of 32. So I could write this as the cube root of 8 times 4, and then break that up as the cube root of 8 times the cube root of 4. The cube root of 8 is 2, and the cube root of 4 is just the cube root of 4. So this would be considered simplified. Let's say I wanted to simplify the square root of 40. Another way of doing this, instead of like pretending like we know exactly what the number is just to completely factor it. So 40 completely factors as 2 times 2 times 2 times 5. And just like 32 completely factors as 2 times 2 times 2 times 2 times 2. And what I see here is that whatever this number here is, whatever that index is, I need that many of the same thing to be able to pull one of them out. So I pulled out 1, 2, right there. And I was left behind with the cube root of still 2 times 2, which is 4. Here, my index is 2, so I have to have 2 of a thing to be able to pull out, right? The square root of 2 times 2 is the square root of 4, which is 2. So this ends up equaling 2 times the square root of, I still have a 2 times 5 left inside there. Right? Neither of those can factor out nicely. This is kind of the very kind of granular way of explaining it. If you're more comfortable doing whatever you've done before to do this, that is perfectly fine. Like, so if I was looking at, say, simplifying, I don't know, the square root of 48, I would probably do it by saying, 48 has a factor of 16, and 16 is a square number. So I can say, oh, this is the square root of 16 times 3. And then the square root of 16 is 4. So this is 4 times the square root of 3. But there are other ways you could do this as well. You could write this as the square root of 2 times 2 times 2 times 2 times 3, and then do it that way as well. Okay. Do whatever works best for you, as long as it works. I don't have time today, but maybe in December, I'll tell you guys about anchor days, because tomorrow is what's called an anchor day. It's October 10th, but I'll have to leave it at that. I'll have to, you can look it up for yourself if you're interested, but yeah, we'll talk about anchor days sometime. Let's see, I'm on the wrong page here. Let me look at this. Sure. Oh yeah, we got time. We got enough time to get through all this. So if you are looking at the notes, you might notice that the blank notes have an extra page and the completed notes do not. So I want to do some simplifying of things because I feel like when I've taught this section before, I haven't done enough examples. So we want to simplify the following. So we're going to simplify the following expressions. What have I got here? Got the square root of 3 times xy to the 5th times the square root of 8 times x to the 9th times y. So the 7th divided by the square root of 6x squared y cubed. And so here's what I would do first. When you have square roots multiplied or divided together, you can combine them all into one square root. So I could rewrite this as square root of 3 times x times y to the 5th times 8 times x to the 9th times y to the 7th over 6 times x squared times y cubed. And then we can do some simplifying. So let's see. So 3 times 8 is 24. X to the 1st times x to the 9th is x to the 1 plus 9, which is 10. Y to the 5th times y to the 7th is y to the 12th. And then on the bottom doesn't change, 6x squared y cubed. And then we're going to divide. So 24 divided by 6 is 4. X to the 10th divided by x squared is x to the what? Sophia, I'm not sure which part you're asking about. I'm guessing you're asking if this was x squared. It is.
No, the top one, Professor. 8x. Yes.
That's a 9.
Yes. 9. Okay.
9. Sorry.
Thank you.
You're welcome. So sorry, I was asking you guys, when we divide x to the 10th by x squared, you get x to the what?
Fifth. No.
So is it 5 or is it 8?
8. 8.
It is 8, right? Because when you divide those things, we don't divide the powers, we subtract the powers. And same thing here, y to the 12th divided by y to the 3rd is not y to the 4th, it's y to the 9th. Okay. What's the square root of 4? 2. What's the square root of x to the 8th? So there's a couple ways you could do this here. You could either say this is the same as 4 times x to the 8th times y to the 9th to the 1/2, which is then 4 to the 1/2, which is the square root of 4, which is 2. X to the 8th to the 1/2, we would multiply the powers, and 8 times 1/2 is 4. So we would get x to the 4th. And then y to the 9th to the 1/2 is interesting. The square root of y to the 9th is not y to the 3rd, because y to the 3rd times y to the 3rd is y to the 6th. So the square root of y to the 9th actually doesn't simplify as nicely as we might like it to. Here's how I'm going to write it for now. I'm going to write this as the square root of y to the 9th, which is y to the fourth times y to the fourth times y to the first. And the square root of y to the fourth times y to the fourth is y to the fourth. And then I have an extra y left over inside the square root. So this becomes 2x to the fourth, y to the fourth times the square root of y. And that would be considered as simplified as possible. You might argue, and some people would also say that you could also write it as 2 times x to the fourth times y to the 9 halves. That would also probably be considered acceptable. The hard part about simplifying things is people sometimes have different ideas about what it means for something to be simplified. So it's very much a kind of, it's not always exactly the same for every person. And people have kind of different opinions about if something is more simplified one way or the other. Okay. Let's look at these next few problems here. Now the next one is to simplify the square root of 18 minus the square root of 50 plus the square root of 32. Now here's the thing. As written, there's no meaningful way to put these together. We cannot add or subtract square roots by just adding or subtracting the insides. What we can do is try and simplify each of these and see if maybe they'll become more similar. So square root of 18 is the square root of 9 times 2. Square root of 50 is the square root of 25 times 2. And the square root of 32 is the square root of 16 times 2. Square root of 9 is 3. The root 2 still stays. Square root of 25 is 5. The root 2 still stays. Square root of 16 is 4. The radical 2 still stays. So now here's what I've got. I've got 3 of a thing minus 5 of a thing plus 4 of a thing. 3 minus 5 is negative 2 plus 4 is 2. So I have 2 of these altogether. An easier way to see this, though, is to factor out the square root of 2. If I factor out the square root of 2, I'm left with a 3 minus 5 plus 4. That's equal to 2. So I have the square root of 2 times 2, which we would not write this way. It just feels wrong. We usually write the whole numbers first. So we would write it as 2 times the square root of 2. That's just the more correct, normal, usual, typical way of writing it. So we can really only add or subtract radicals together if they happen to have the same exact thing in the radical. Otherwise, you're kind of just stuck. So if someone says, like, what's the square root of 5 plus the square root of 6? Or to simplify the square root of 5 plus the square root of 6, you'd be like, I'm done. That's it. You can't simplify that anymore. That's all you get. Okay. Last couple examples on this page. So we've got, I want to simplify the square root of 12 plus the square root of 3 squared. And I don't think the intention here is to simplify the inside first, although we totally could. I'm going to do it the long way, even though you could totally simplify a square root of 12 as 2 times the square root of 3. But I'm going to show you the long way because I think that's really what's desired here. So whenever you're squaring a thing, you're just multiplying it by itself, right? Twice. Just like when you're cubing a thing, it's something times itself 3 times. So now I have to, since I'm squaring this, I have to FOIL it out. So everybody, what's the square root of 12 times the square root of 12?
12.
Yeah. Whenever you multiply a square root by itself, you get just the thing. What's the square root of 12 times the square root of 3? So when we multiply square roots together, you just multiply the insides together. 12 times 3 is 36. And I get that there. I also get it here. And then the square root of 3 times the square root of 3 is 3. Now this one happens to work out nicely. 36 is, sorry, the square root of 36 is just 6. So I get 12 plus 6 plus 6 plus 3, which is equal to 12 plus, let's see, 12 plus 6 is 18, plus 6 is 24, plus 3 is 27. Okay. So another question is to simplify an expression like this. Now, often when someone says simplify, one of the things that is implied is that we have to rationalize the denominator, meaning we don't want any radicals in the denominator if at all possible. And for a problem like this, the only way to get the radical out of the denominator is by multiplying by the thing called the conjugate of that square root thing. So we're going to multiply. Well, what's the only thing we're allowed to multiply by and not change anything? 1. So we're going to multiply by 1. We're going to multiply by we're going to multiply by 1. In this case, we're writing 1 as the square root of 7 plus 2 over the square root of 7 plus 2. On top, we just get 6 times the square root of 7 plus 2. And I might multiply that out, but I'm going to wait a second to see if I can cancel anything first. On the bottom, here's what we get. All right, what's the square root of 7 times the square root of 7? 7. And now here's something really, really important. This is why we multiply by the conjugate. Square root of 7 times 2 is just 2 root 7. And negative 2 times root 7 is minus 2 root 7. And those middle terms exactly cancel each other out. So the whole reason we multiply by the conjugate is so that you don't have any more radicals left. And then negative 2 times 2 is minus 4. So I end up here with 6 times root 7 plus 2 over 7 minus 4, which is 3. And then 6 divided by 3, I can cancel a 3 here and a 3 here, and be left with a 2 on top. So I could write this as 2 times root 7 plus 2. Or I could even distribute the 2 and get 2 root 7 plus 4. Either way, I think would be fine to write your answer here. Okay. So that is some examples of simplifying things. Let us talk now about logarithms. I will fully admit, when I first learned about logarithms, when I was a student, I found them challenging. It takes a little bit of time to wrap your head around what exactly a logarithm is. But we're going to talk about it. So first, we're going to look at solving these equations. So 2 to the x equal to 8. What's the power there? 2 to what power equals 8? 3. 2 to the third equals 8. And in a similar way, we can say that if 2 to the x is equal to 32, that power is 5, because 2 times 2 times 2 is 8, times another 2 is 16, times another 2 is 32. That's 5 2's multiplied together. I'm going to leave myself a spot here. I'm going to say 2 to the x equal to 64. 64 is the next power of 2. Right? 2 to the 5th is 32. If you multiply 32 by 2, you get 64. So 2 to the 6th is 64. But then we want to be able to answer the question, if 2 to the x equals 40, what is x going to be? Well, we know it's not 5, and we know it's not 6, because 2 to the 5th is 32, and 2 to the 6th is 64. So 2 to the x equals 40 is not a whole number. It is between 5 and 6. So here's the deal. And here's the example that I really do keep in my head all the time. 2 to the third equals 8 has an equivalent logarithmic form. And the equivalent form is that log base 2 of 8 equals 3. And I really encourage you, when you write down a logarithm like that you say those words. Don't just say log 2, 8. Say log base 2 of 8 equals 3. It'll help you remember what things really are. Right? The base is 2. It's equal to 8. And then you get 3. So when I read this, I do say those words. I say log base 2 of 8. But then the other words I say in my head, when I see this, I'm going to use a different color here. The words I actually say in my head are 2 raised to what power equals 3. Sorry, no, it equals 8. Geez, sorry. Blew it. Sorry, the question that, so when I see log base 2 of 8, the question that I actually hear in my head is 2 raised to what power equals 8? And then the answer is 3. Something you will hear people say is that a logarithm is just an exponent. And it is. The logarithm is the exponent that we raise 2 to get 8. In a similar way, 2 to the x equal to 40 has an equivalent logarithmic form. It's log base 2 of 40 equals x. Now in this case, there's no nice number here. Log base 2 of 40 is the number. And you can use a calculator to get an approximate decimal, you can get a decimal approximation of this, but it's an irrational number, right? Kind of like how the square root of 2 is irrational or pi is irrational, right? It's got a never-ending, non-repeating decimal. So log base 2 of 40 is the number you raise 2 to get it equal to 40. A few notes about logarithms. So we abbreviate some logs that come up a lot. We live in a base 10 world, right? I mean, not that everything is base 10, right? Time is kind of base 60, but base 10 is like most of the stuff we deal with. So log base 10 of x is written as just log of x. We omit the 10 because we're just lazy, because we're trying to save ink when we write our books and we don't want to write all those little 10s in there. In a similar way, log base e of x, where, in case you didn't know, e is the natural base. It's approximately equal to 2.7. We'll talk more about e on a different day, but for now, just know it's an irrational number. It's about 2.7. We write this natural log of x. Some people like to say ln of x. I do not personally. I used to have an office right next to someone whose name was Ellen. Really, truly, I did. And so whenever I would say ln of x, she was like, "Are you talking to me, James?" I'm like, no, sorry, Ellen. I'm not saying ln of x. I'm saying natural log of x. So I will say natural log. I encourage you to say natural log. I think it sounds better, but I know it is more syllables to say than ln. So whatever you want to say is fine. What else? We can only take logarithms of positive numbers. Right, so if I wanted to take like the log, so I could not take the log base 2 of, say, -8. This is undefined because there is no x, so that 2 to the x equals -8. There's no solution to that. Right? There's 2 to any power is always going to give you a positive result. And so there's no way that 2 to the x can equal a negative result. It's also true that you can't take a logarithm of 0. So for the same reason, log base whatever, pick any base you like, log base 3 of 0 is also undefined for the same reason. So another way to say this, running out of room here, I'm going to erase the top stuff here. Another way to say this is that the domain of log base b of x is that x has to be positive. So that x is strictly greater than 0. Or if you prefer the interval notation, it's everything from 0 exclusive to infinity. Okay. Yeah, we should be able to get through the rest of this. I know we're almost out of time. We got 7 minutes, plenty of time to talk about some logs. So probably the number one thing you want to be able to confidently do with a logarithm is rewrite it as an exponential equation. So if I was asked to find or evaluate the following, here's what I do. So if I want to find log base 7 of 49, again, the words I'm going to ask or say in my head are 7 raised to what power equals 49? What do you guys think? 7 to the what equals 49? I think I saw some people do that. It is 2. Be careful. I've definitely seen people accidentally say the answer was 7 because they said, oh, 7 times 7 is 49. But we want 7 squared, or 7 to the second power equals 49. So you can either just say the answer is 2, great. Or if you didn't know right off the top of your head, you can say, okay, well, I'm not sure. So log base 7 of 49, I'm going to say it's equal to x because I don't know what it is. And then I'm going to rewrite this. I'm going to rewrite this as 7 to the x equals 49. And then I can say, oh, 7 to the x equals 49 is 7 squared. So if these two things are equal, x has to equal 2. So log base 7 of 49 is 2. You're welcome to show more work. You're welcome to show a little less work, depending on how easy or hard it is. Okay, let's look at this next one. Log base 2 of 1 over 64. I don't know what that is. So I'm going to say it's equal to x. Again, I do know that I'm saying 2 to some power equals 1/64. It's probably going to be interesting. So I'm going to rewrite this as 2 to the x equals 1 over 64. And then I'm going to try and express 64 as a power of 2. And I think I erased it. Yeah, we're too far. But we saw before that 2 to the 6th was equal to 64. So I could say that 2 to the x equals 1 over 2 to the 6th. And then 2 to the x equals, how can I write 1 over 2 to the 6th? So that it's 2 to the, what goes up there?
-6.
Thank you. And now that they're both written as things with the same base, we can say that the powers have to equal each other. So log base 2 of 1 over 64 is -6. So 2 to the -6 power is equal to 1 over 64. Right. A couple more here. Yeah, we'll get through these. I might need an extra minute or two at the end, but I will try to work as quickly as possible. The next one's actually real easy. Log base 7 of 1. 7 to what power equals 1? The 0th power. Anything to the 0th power equals 1, right? So I can also write it as log base 5 of 1. That's also equal to 0 because 5 to the 0 equals 1. And this is true because 7 to the 0 equals 1. So whenever you're taking a logarithm of 1, it's always equal to 0 because anything to the 0th power is equal to 1. Okay, now we get to the ones that are a little bit trickier, like log base 8 of 4. So we're asking 8 to what power equals 4? And I want to warn you before we get going here, the answer is not 1/2, right? Again, one could think that the answer was 1/2 if they're making the mistake of saying 8 times 1/2 equals 4. But I'm asking 8 raised to what power equals 4? So since I don't know the answer, I'm just going to say, well, I'm going to say it's x. And then I'm going to immediately take my logarithmic equation and rewrite it as an exponential equation, 8 to the x equals 4. And then I'm going to rewrite both sides, if possible, as powers of the same common base. 8 and 4 can both be written as powers of what smaller number?
2.
Yeah. 4 is 2 squared, and 8 is 2 cubed. And then I can use one of my exponent rules to say that 2 to the third to the x, I'm going to multiply those powers. So this is 2 to the 3x equals 2 squared. And then once again, we see that if two expressions have the same base, for them to be equal, the powers have to be equal to each other. So we have that 3x is equal to 2, which means x is equal to 2/3. So log base 8 of 4 is equal to 2/3. All right. So let's look at this next one. Log base 16 of the 7th root of 1/32. Wow, that looks very complicated. I'm definitely going to rewrite that. So I'm going to say that that's equal to x. And then my base, so again, here's why I say log base 16 of this stuff, because I know that my base is 16. It's equal to x because the logarithm is the exponent. And then it's equal to this mess here. Okay, so I'm definitely going to try and write both of these sides as powers of a common base. 16 is 2 to the 4th. And this is, all right, so first of all, 32 is 2 to the 5th. So I'm going to write this as 1/2 to the 5th. And instead of writing it as the 7th root, I'm going to write it as the 1/7 power. And then I'm going to bring up the 2 to the 5th as 2 to the -5th, still to the 1/7 power. On the left side, I'm going to multiply those powers. So I get 2 to the 4 times x. On the right side, I'm going to multiply those powers. And I get 2 to the -5 times 1/7 is -5/7. Those have to equal each other. So 4x equals -5/7. Divide both sides by 4, or multiply both sides by 1/4 to get that x is equal to 1/4 times -5/7. So x equals -5 on top, 28 on bottom. And that's what the answer to this particular question would be.